This lecture will show how we can use the orthogonality of the eigenvectors that we've learned how to find for multi-degree of freedom systems to solve free response problems. We'll do the derivation for a general system and then look at some examples. So, previously we talked about the fact that by assuming a solution of the form x of t is the real part of some vector, e to the I omega t, that if we had just the right frequency, this would indeed be a solution to the system. And importantly then, the response of the first degree of freedom in x, the x vector, was proportional to the first element in phi, and the second one, the second, the third, and so on. So anyway, this vector phi gives us the shape of the response of the multi-degree of freedom system. And an n degree of freedom system will have n of these solutions, each of which has a natural frequency omega and an eigenvector phi. And we initially found those as unscaled vectors. The book proves that you can, that if you compute a dot product between the jth eigenvector and with the mass matrix's weighting and the nth eigenvector, that this will always be 0 if j is equal to n, or is not equal to n. And the same is true for the stiffness matrix. So these vectors are not only special solutions, but they're an orthogonal basis for the solutions of the system. What do I mean by orthogonal? Well, let's just review math really quickly here. Remember that two vectors are orthogonal if they have a 90-degree angle between them in a two-dimensional or three-dimensional space. And there's a test for orthogonality involving the dot product. If we take the dot product between two vectors x and y, if that dot product is equal to 0, then the vectors are orthogonal. And you can see that in this simple example. Depending on the notation you've used in math before, we could write this as I plus j, and this vector down here as I minus j. And when we dot these together, we'd have I dotted into I, which is 1, and j dotted into j, which is minus j, which is minus 1, or we get that showing that they're 0. For this class, the more relevant definition of a dot product is that you take one of the vectors transposed into the other. So here we would write this vector as a 1, 1, this one as a 1 minus 1, and then the dot product is just the product of these two, which would give us 1 times 1 minus, or plus 1 times minus 1, which is also equal to 0. So that's orthogonality, and this definition is extendable to the case where these vectors have an arbitrary length. Once we're beyond 3 dimensions, we can no longer visualize it in a plane or a 3D space, but the same orthogonality property can be used. There's another difference in that we're not saying that the vectors are directly orthogonal, but we're saying that they're orthogonal when multiplied through a weighting matrix. And our weighting matrices, M or K, are always symmetric. And so you can think of that as basically taking these coordinate axes and skewing them. Let's say we skewed the y-axis here at an angle. Now the weighting matrix accomplishes that skewing, and it will we'll now be finding orthogonality on these skewed x and y axes. And so that's what happens here. But whether we have orthogonality with respect to a weighting matrix or direct orthogonality, the result is the same in that the vectors we can separate, or we can break the equation into independent parts. In Cartesian space, we might have one equation for the x direction and one equation for the y direction. They're both independent. We can solve them independently. The same is true on these skewed coordinates. Before we go forward, though, it's helpful to normalize the vectors so that we get a cleaner answer. And so we usually do that with respect to the mass matrix. If we take the jth eigenvector unscaled, transpose times m times that same eigenvector again, we'll get some number. And we call that mu sub j. And you can pretty easily see that if we define a new vector, this is the scaled eigenvector, or we call this one mass normalized, then if we just divide that vector by the square root of mu, then we'll have 1 over square root of mu here, 1 over square root of mu here, and that will cancel so that we get a 1 over here. So that's all that there is to that. We scale the vectors in that way. If we do that, one nice thing that happens is that if we take the jth eigenvector and transpose k times the jth eigenvector again, so it's the same one both times, then what we get is the corresponding jth natural frequency. So this allows us to put the equation of motion in a really simple form. And we do that by replacing our vector x in the original equation of motion that we have down here with a matrix phi times eta, where the columns of phi are the mass normalized eigenvectors of the system. So we put each of those in the columns, and if we then substitute this in for x in this equation down here, we'll get m times phi times eta, k times phi times eta here. And we aren't quite ready to use this development of orthogonality because we just have half of it. We have just the left or the right half here, but we're missing the phi transpose. So what we do is we pre-multiply this whole equation by phi transpose. And if we carry the phi transpose through into each term, we get phi transpose n phi, eta double dot, phi transpose k phi, and then we also have to phi transpose times the forcing. So our equation of motion, we can now exploit the orthogonality, and it's maybe not immediately obvious that this equation is better, but if we use the relationships from chapter 4.2.2, if we use these orthogonality relationships, we can show that this matrix, this product of matrices, is just an identity matrix. And this product of matrices is just a diagonal matrix with the natural frequency squared on the diagonal and zeros everywhere else. And then over here, let's see, these down here I'm writing the unforced case, but that's not exactly correct because we want to have forcing. So I can just barely squeeze that in. But write that a little neater for you here. Okay, but in any event, now we have a set of uncoupled equations. And now, if we take the first term on the diagonal here, this one here, it multiplies the first element in eta double dot and eta. So that will give us that would give us just eta 1 double dot plus omega 1 squared eta 1 is equal to the first eigenvector transpose times the force. So in the same is true for any element along the diagonal. So each equation it can be written in this form, and the only thing that changes from equation to equation is the index. You go from j equals 1 to 2 to 3, and each equation involves the jth natural frequency only and the jth eigenvector only. So no matter how big a system is, this could be a 1 million degree of freedom finite element model, or it could be a small little system as we've done before. But no matter what we have, we end up with a set of uncoupled equations. And each one is independent, and its properties depend on that mode only. So let's look at an example here. Our favorite 2 degree of freedom system, if the mass and stiffness are both unity. We found previously that the 2 natural frequencies were 1 and the square root of 3. These were the 2 unscaled mode shapes. If we went through that process we just talked about and scaled them, because the mass matrix is an identity, it's pretty easy to work out that the scaled mode shapes are 1, 1, 1, minus 1, with a 1 over square root of 2 in every term. So I just put that outside to simplify things. So if we want to solve for the free response of this system, we can use this transformation now to uncouple the equations. So again, we'll plug in, pre-multiply by phi transpose, and oops, there's a phi transpose missing from this term right there. And here it happens that the phi matrix is symmetric. This is phi transpose in phi. And let's look at some of these directly. So this is just an identity times phi. So that's going to do nothing to the equation. Let's look at the first element though in this product. For the first element we take these times these. So we get 1 times 1 plus 1 times 1 is equal to 2, right? And similarly, if we take that same row in this column, there we get 1 times 1 plus 1 times negative 1, or that's going to be 0. So that's this term right there. Right? So anyway, we see the orthogonality happening right here, and so we get a diagonal matrix for the mass matrix, and after we multiply by the 1/2 factor, this is just 1, 1, 0, 0, or it's just a 2 by 2 identity matrix. Alright, and if we do the same thing with the stiffness, here we're putting the stiffness matrix with phi transpose k phi. We do the same thing there. Now what we have is a diagonal matrix with the first natural frequency squared, the second natural frequency squared, the zeros on the left diagonals. So if we plug those into our equations of motion, what we now have, our 2 equations are now uncoupled. See, originally we have this top equation would have x1 double dot plus 2x1 minus x2 equals f1 of t. So this is a coupling term between the x1 coordinate and the x2 coordinate in this first equation. And we can't just look up that equation in a book and find the solution for it. These, though, are now uncoupled 1 degree of freedom systems. We spent a long time learning how to solve these, and so now we can apply anything that we've learned previously to solve these 2 uncoupled equations. So this derivation is one of the most fundamental derivations in vibrations. I expect you to know it. You should be able to make this substitution, plug it into an equation, and work out what the uncoupled equations of motion are. From this point forward, we'll learn this so well that we might sometimes just skip ahead and say, well, we know that if we plug this into our equation of motion, that the result is going to be a set of uncoupled equations that look like this. And so we might sometimes skip all of the details. but we'll come back to that later. There is something interesting going on the right-hand side. Notice that the forcing for equation of motion 1, or for mode 1, is not just the force on mass 1. This is the force on mass 1 plus the force on mass 2. And it turns out in this case, the average force, the sum of those two, it's kind of like the average force, so the scaling is not quite 1/2, is the forcing that mode 1 feels, where mode 2 feels the difference force, the difference between those forces. And that makes sense if you go back here and you remember that mode 1 has them moving in unison, right? So what it really is sensitive to is the sum of those two forces. Mode 2 has them moving in opposition, so it's most easily excited when those two forces are equal and opposite. Alright, we'll get back to forces later. Let's first just see what happens with a transient response. So again, we have our two equations. If we want to find the transient response, what we will need are some initial conditions. And we might be given the initial conditions on the generalized coordinates. Here I'm using Q1 and Q2 as the book uses for those. And we can assemble those into some 2x1 vectors of the initial displacements and the initial velocities. And so those are our knowns, but we need to map those to the modal coordinates to be able to solve these equations. These equations don't know about the q's. So we can easily do that. What we do is we take this equation and we just invert it. So if we knew q at time 0, we can multiply by the inverse of the phi matrix to get eta at time 0. And one neat property that we can use that makes this a little easier is to recognize that since phi transpose m phi is an identity matrix, that this right here has to be the inverse of phi. Because anything, the inverse of anything times itself is always an identity matrix. So that's the definition of an inverse. And okay. So if we, let's not go there just yet. Ignore this part for now. So we can get our initial, actually, sorry, this is okay. We can get our initial conditions on Q by multiplying both sides by phi transpose m, both sides of this top equation, which tells us that eta 0 is phi transpose m times q. Alright, and then once we get done with that, we know what we need to know. We know eta 1 of 0, we know eta 1 dot of 0, and so now we know that eta 1 of t has to be some constant times a cosine and some constant times a sine. Notice that the equation for eta 1 right here involves the first natural frequency squared, so that's the frequency of oscillation in this free response. And so we just have to find A1 and A2 to satisfy the initial conditions. Similarly for mode 2, and notice that it's oscillating at its own natural frequency. So let's take an example. Let's say our initial condition was 1, 1, or in other words, at time 0, we displace this mass, we move it to the right by 1 unit, and then we move this one to the right by 1 unit, and then we let them both go. So this would be true at t equals 0, then we let them go so there's no force applied to them after that. And because they're initially at rest, the velocities are both 0, so we can tell right away then that Okay, one thing that's interesting about this problem is that this happens to be proportional to one of the mode shapes, right? So our initial condition is actually some constant, and in this case that constant is just the square root of 2, some constant times the first mass normalized mode vector. So plugging that in, what we can show is that if we were to plug in for the phi matrix the two columns, these two vectors, phi transpose m phi, to do the multiplication, we can treat each block as if it was a matrix, as a scalar in the matrix. So the transpose of this matrix is just phi 1 transpose. So now it's in the row, phi 2 transpose. And now we just evaluate that product, and it's just like multiplying scalars. So the top will be phi 1 transpose m phi 1. The bottom will be phi 1 transpose m phi 2. And so this, because of orthogonality, that the two vectors are orthogonal with respect to mass, so that gives us a 0. So our initial condition is C0. So we can use that to say, if we set eta 1 at time 0, which is this equation, the sign vanishes, and that tells us that the magnitude of the cosine term is A1. Eta 2 has to be 0 for all time because it has no initial displacement. But, well, that gives us that E1 is equal to 0. Eta 2 dot is 0. Because Q is this vector of zeros, anything times 0 is still 0. So that basically is going to tell us then that A2 is equal to 0 in the first equation, and that B2 is equal to 0 in the equation for mode 2. So plugging that all in, our solutions up here have become way simpler. They're just C1 cosine omega 1t. 802 of t is just all 0. So we could say we're done now, right? But we're actually not totally done, because we found the modal coordinates as a function of time. But as we set out, what we really probably wanted was to know what Q1 and Q2 were going to do as a function of time, or what the two masses were going to do. So we have to use this equation to bring us back to physical coordinates. So we do that here. Q of t is just this matrix phi times eta 1 of t, eta 2 of t. And using this same partition idea, we can actually break that into two terms. We can say that this is the first mode shape times eta 1 of t plus the second mode shape times eta 2 of t. So here you can explicitly see how we have some vibration, eta 2 of t, which is a cosine, or eta 1 of t, sorry, vibrating at its natural frequency. So we have that motion in modal coordinates. In physical coordinates, this matrix, which has a 1 and a 1 in each of those elements, will get masses 1 and 2 both moving in that same shape. And we'll have no response from mode 2. Alright, so that's everything there. Let's look at what this looks like in Matlab. Here's an example. We have our mass and stiffness matrices. We have our initial conditions, Q0, Q dot at time 0. And in Matlab, to solve the eigenvalue problem, we just type phi, and we just use I of k and m. That gives us a diagonal matrix of natural frequencies, so we have to take the diagonal and then the square root to get the actual natural frequencies. And we can check that Matlab mass normalized the mode vectors correctly. So let's let's take it just to that point at first. So if we run this and we look out here, here's the phi matrix. Notice this is the negative of the eigenvector that we got, but it's still a valid eigenvector. It'll affect the sign of eta 1 of t, but not the final answer, because the negatives will cancel. But anyway, here are two natural frequencies. Here's the phi. The product phi transpose in phi is identity as we hoped. We can do the same thing for phi transpose k phi. That's 1, 3, just like we found earlier. Alright, so now we can use these equations to get eta at time 0, eta dot at time 0. And then, rather than using the special cases that we just did, I wrote this generally. So we could then show that A1 is eta 1 at time 0, B1 is eta 2 at time 0. And the velocities, we'd end up getting the coefficients on the sine terms are the initial velocities divided by the respective natural frequencies. So omega n's is a vector that has both of those natural frequencies in it. Alright, so I define a time vector, and now I've constructed a matrix eta of t. Let's just look at what's happened up until here. So I've created a matrix eta of t that's a 2 by 87. So let's just look at the first 5 elements. Oops. So this is the initial eta, and then this top row shows how eta 1 evolves with time, and the bottom row shows how eta 2 evolves with time. The nice thing about doing that is I can now multiply by phi, and it will operate column by column on this. So at each instant in time, see, the columns are the instants in time. My time vector is 87 by 1, so I have 87 time instants, which is why this was 2 by 87. Anyway, the phi matrix will operate on each column of that one at a time. And what I get is the modal response versus time. And if I just multiply by phi, I get the physical response of the two masses versus time. So now if I run the whole thing, I get a plot. This top shows the two modal coordinates. Mode 1 is a function of time, which is just a cosine, and mode 2 versus time, which is always 0. When I multiply by the mode shapes, now I get that mass 1 and mass 2 are both moving always in unison, and they're always moving at the first natural frequency, whose period is 2 pi. The natural frequency is 1 radian per second, so the period is 2 pi over 1. So that's how you would implement this. If for some reason we don't believe this or we don't trust it, we could run this part to overlay the solution using ODE45. And so it's overlaid onto the curves, and it gives you the exact same thing. ODE45 knows nothing about modes. If you look in here, the equation of motion, it has these full matrices, n and k, there's coupling. It's solving those equations at each time step, accounting for the coupling between the degrees of freedom. But it gives us the exact same answer. Alright, so we can look at some other cases just to see what happens here. So that was the special case where our initial condition was in the shape of mode 1. What if we have an arbitrary case where we just take the first mass and we displace it by a certain amount? So for this example, let's say we displace this first mass a certain amount, but we leave the second mass at its equilibrium position. and then we let the system go. What happens? Right. So if we run this again now, after making that change, now what we see is that both eta 1 and eta 2 are cosines with time. Eta 2 is oscillating at a higher frequency because it has a higher natural frequency, but they're both simple cosines in time. In contrast, the two masses were starting with mass 1 displaced 1 unit, mass 2 at equilibrium. But when we release from that, the superposition of these two modes causes the two masses to do some really interesting and complicated things. They're bouncing back and forth, they're pushing on each other. Initially, mass 2 is at rest, mass 1 is being pulled back to equilibrium, where 2 is being pulled away from it, and it's pushed away from equilibrium. Then 1 shoots fast to the negative side, and that causes this complicated interaction. So we can take something really complicated like that, and we can break it down into these simple motions. So that's the power of modes and modal analysis. And again, that holds for simple systems, and it also holds for really complicated systems. So this is a finite element model with tens of thousands of degrees of freedom. And I should give a disclaimer, this isn't a real finite element model. This is just something we threw together to look like the space launch system. It has none of the actual complexity. This is basically just hollow metal shells with about the right shape. But anyway, this does give you kind of a qualitative idea of what the modes of a rocket might look like. So this is the first mode, second mode, a torsion mode. And so each mode would be oscillating in a simple way. If we were to pluck the top of the rocket, maybe give the rocket some initial displacement in the launch abort system up there, what we might see is a superposition of motions, with this mode vibrating at its frequency, this mode moving at a higher frequency, and on up until we include all the modes that are significantly excited. So this complicated vibration we could understand in this same way, as a superposition of a bunch of modes, each oscillating at progressively higher frequencies. When we put them all together, the whole rocket's going to do some really complicated things. But this gives us a path forward to computing that. Alright, so that's everything on modes and orthogonality for now. Next time we'll talk about how to solve forced response problems.